So hi everyone. Today I'm going to present what I originally gave as a live lightning presentation at a mineral prospectivity and exploration conference. This is just going to be a slightly longer version of that presentation, which was only 5 minutes. So I'm going to talk about what happens when we want to use machine learning for mineral potential mapping, but we have a lot of input targeting criteria that we want to include in the model, but we actually have very little training data available. Right, so as I'm sure a lot of people understand, machine learning techniques can require a large number of training data to effectively train the model. And as these models get more complicated, the more training data we need to effectively train them. Right. And as mineral occurrences are rare events, there's not a lot of them, and economic mineral occurrences are obviously even rarer than that. So what I've found from reviewing the literature is that most published models seem to be kept relatively simple, including maybe a dozen or so input maps. There's very few that include more than 20 or so. But we do have, as geoscientists, very large volumes of data. And so by only including a dozen or so input maps, a lot of that data is therefore going underutilized or unutilized entirely because we don't have enough training data for more complicated mineral potential maps or models. Right. So what I'm going to talk about is efforts have been made to come up with solutions for this lack of mineral deposit training data for mineral potential mapping. However, they're typically making assumptions about the nature of the mineral system being targeted, and some certain types of input maps don't hold up to some of these assumptions because of the way the data augmentation actually works. So going to the next slide. So the data augmentation problem. Basically, as I was saying, the more unique conditions or feature vectors that the model has to generalize, the more training data we need to effectively do that generalization. Right. So methods like SMOTE or addition of noise get used to increase the size of the minority training class. And in mineral potential mapping, the minority training class is the mineral deposit class. We simply don't have enough known mineral deposits ever really to effectively train really complicated models. So we need to find a way to increase the size of that minority class. But what happens is these methods assume that the neighboring classes share the similar characteristics to the class that contains the original known deposit, which is highlighted in these examples on the screen here. So on the left, we have buffered intrusions. If our original deposit is 200 meters away from a known intrusion, we can safely generally assume that putting an augmented data point at a 300-meter buffer distance is probably close enough geologically to having it at the 200 meters. So our original point's at 200 meters, our augmented data point is at 300 meters. That's okay, right? That works for that particular mineral system where the buffered intrusions are an important targeting criteria. Right, so using the same base data, but we're targeting a different mineral system where the host rock is important. Right, the neighboring class to an I-type intrusion could be a sedimentary unit. Unfortunately, an I-type intrusion is not similar to a sedimentary unit. So in this case, the neighboring class here is actually not similar geologically to the original class. So if our original training point is in an I-type intrusion, as it would be for a porphyry copper gold mineral system, putting an augmented data point in the neighboring class, which could be sedimentary, is not geologically valid. It's putting it into a non-permissive geological setting, right? And so even though it's, as we can see, same input data, same intrusions, but the input map actually depends critically on the mineral system that we're trying to target. One, the host rock is critically important. One, the having the presence of an intrusion is important, but it doesn't necessarily have to be hosted within the intrusion, right? So having these ordered numeric maps, whether it be increasing buffer distances or decreasing density values or decreasing element concentrations for geochemistry maps as we're moving away from the original source data, that works for probably most mineral systems, right? But it doesn't work for all of them. It doesn't work for mineral systems where it is the host rock or some characteristic of the host rock. So whether it's lithology or stratigraphy or magma fertility, where the features are not in any kind of numerical order. Categorical type data, right? So this became a problem in the case study that I was working on, which was examining the porphyry copper gold mineral system in the Macquarie Arc in Australia, where I was looking at using random forests and neural networks to try and target this mineral system using different sets of input maps. So one set of input maps there were 197 maps, and they hadn't had any favorability criteria applied in terms of buffer thresholds or density cutoffs or anything like that. And the second set of input maps was 164 binary input maps, where these favorability thresholds had been determined using some weights of evidence statistics. So the models were trained using 14 economic porphyry copper gold occurrences and 14 non-deposit locations. So this augmentation issue, it doesn't really relate to the non-deposit locations because they can be randomly generated and easily randomly generated to create as many as we need to match the number of known deposits. And then we had a separate subset of data for using that for validation purposes of the model. Right. But the problem was that each of these models contained over 30 categorical input maps, primarily relating to the host rock magma fertility. Now, the reason there were 30 was we were looking at different magma fertility parameters based on different whole rock geochemistry values and ratios. And what we found was all except the 164 binary map random forest model showed quite a severe amount of overfitting, although the neural network models were both far worse than the random forest model. So what's the solution to this, right? I don't have the solution. I have a couple of ideas about what actually needs to be addressed to come up with a solution. I've thought about this quite a lot, and I think there's two issues primarily that need to be addressed. One is, how do we deal with the data augmentation methods when we have categorical input maps where the host rock is critical and we're not buffering things necessarily? So one, we can use the data augmentation methods as they are and basically just remove any new deposit sites that fall in non-permissive geological settings. There's obviously some pitfalls to that approach. If the geological mapping is incomplete, which it almost always is, what's going to end up happening is we're going to intentionally be removing all training points, and we could be removing the augmented training points, where there is an unmapped intrusion, for example, right? And so it could then end up failing to highlight those areas because it's not learning anything about those areas where we do have incomplete mapping, and we don't know that it's incomplete, right? And this is going to be exacerbated as we include more categorical input maps into our model. The second pitfall to that is we still run into the problem where there's too many unique conditions and we still don't have enough training data, right? because what ends up happening, these augmentation methods are still learning too much from the small number of known deposits that are used as the basis for that augmentation. So say we start out with 15 porphyry copper gold occurrences, want to augment that to 150. Those 135 augmented points are still fundamentally based off learning from those original 15. And so if we've got 10 million unique conditions, which isn't impossible, we've still only got 150 training points, or 300 by the time you include your non-deposit training data, right? That's still quite a limited amount of training points. The second approach, obviously, is to reduce the complexity of the model by reducing the number of unique conditions. And that's what I've done in this example here. These are the two neural networks mineral potential maps. The one on the left is where I used the non-thresholded input maps, so the ones that hadn't had any favorability criteria applied. The one on the right is the one where I've used the binary input maps that had that favorability threshold applied. You can see there is almost effectively no variation in the prospectivity across the Macquarie Arc study area for the model on the left. There are a few pixels in the entire study area that have a lower prospectivity value, but basically it's also essentially useless for exploration targeting, because about 50% of the study area is coming up as prospective and it's not actually useful. The model on the right is slightly better, but you can see there is still very little variation in the prospectivity values across the study area. So it's better, but it's still too complex. There is still not enough training data to effectively generalize this model. So reducing the complexity of the model by reducing the number of unique conditions is an approach that can be used. However, we don't want to risk oversimplifying the model and losing that critical detail, which is really important for characterizing the mineral system, as well as targeting new mineralization for that system. So, as I was saying, it's still a work in progress. I don't have the solution, but I think whatever the solution is needs to integrate both of these challenges, one being the lack of training data and augmenting our training data for mineral systems where we are using a number of categorical type input maps. And secondly, reducing the complexity of the model without losing that really important detail, which is going to help us with our exploration targeting. So I'm leaving this kind of as an open-ended research problem, and it's something that I'm working on in my spare time. But yeah, I think these are really important issues that need to be addressed if we really want to be running big data type models, as opposed to the relatively simple ones that are typically being published at the moment. So anyway, I'll leave it there, and thank you for your time.